Okay, let's do this. So kinetic model theory. Okay, and right. So first of all, we need to understand that there are three states that we need to look for. Okay, so we got solids, we got liquids, and we got gases. Okay, I'll write it here. Let's give it some space. So basically, solids have, like, when it goes from solid to liquids, it's basically called melting, and if it goes from liquid to gas, it's called boiling. On the other hand, if it goes from gas to a liquid, this is called condensation, and goes from liquid to solid, this is called freezing. Very good. You can also call it solidification, that's the same thing, right? Now in reality, how they look like is that solids are like arranged in a very beautiful, nice pattern like this. Very nicely arranged actually. And very close to each other, like almost touching. They are touching, but liquids basically stay in layers and groups. So they're like this. Whereas gases are completely free and they're always like going here and there at high speed. Okay. Now we need to learn their properties. For that reason, we need to see that solids have a fixed shape. Also, they have fixed volume. Now, they have very strong intermolecular forces between them. Okay. Now, basically, they vibrate at their fixed places if you heat them, right? So they keep on vibrating, they don't just move. All right. Now, compared to the other things like liquid has basically no fixed shape. Because when you pour it into any container, it would take the shape of the container. However, liquids have fixed volumes, so they still stay the same. Then, when we talk about intermolecular forces, they have strong intermolecular forces. Not very strong like solids have, but they still have strong. This is the reason they have fixed volumes, right? So they can slide over layers and can move around as well. Is it clear, everybody? They're not fixed like in solids. Now, about gases, they do not have any fixed shape, so no fixed shape, and no fixed volume. So you can actually put them in a container with a smaller volume, they'll fit in, and if you let them loose in your room, they will fill up the room, so they don't have any fixed volume. They have little to none intermolecular forces. They're always going here and there randomly. This is the reason they are randomly moving at high speeds. So they do not basically vibrate, they do not, move in groups or layers. They are free to go everywhere. Is it clear, everybody? Now, so we need to understand that the temperature basically has a effect on these. Like in this one, in solid, increasing temperature would cause stronger vibrations. In liquids, increasing temperature causes particles to move and vibrate faster. In this one, increasing temperature increases the speed of particles. Is it clear? So particles could be like molecules, ions, electrons, whatever, right? So that happens with temperature. So what we learned from this is that basically we must understand, let's write a note here. As the temperature increases, the average kinetic energy, which is also, related to speed of the particles, increases. Okay. Now, what if the temperature decreases? What happens then, right? Of course, we should understand that the speed will decrease, right? But can there be a temperature where the particles might have no energy, kinetic energy left? So there is one, which is called the absolute zero temperature. Now, absolute zero temperature is known to be 0 Kelvin or minus 273 degrees Celsius. Let me write Celsius, right? Which is a very low temperature. Do you know what is the temperature of your freezer in your house? Nobody knows? No. the temperature in your freezer where you know put food and then it can survive for a couple of weeks, that's minus 25 and it's like very cold. So imagine minus 23. So what happens at minus 23? That's the question. At it's minus 273. Okay. So at absolute zero temperature, the particles have the least to none kinetic energy left. So they actually stop vibrating. So nothing can survive in this temperature, at this temperature. Is it clear, everybody?
Yes, sir.
Okay, you can write this down, please. Now, so since we learned that it happens with temperature and other stuff, so we can also look at things like pressure and what is basically happening when you increase temperature or you increase pressure and stuff like this, right? So the biggest question is that how does pressure change occur in a gas? So let's talk about it. Okay. Now, first of all, when the particles hit the walls of the container, they cause a force on it. So the particles are always exerting some pressure on the container, because if there is force and the container wall has some area, so they must be exerting pressure, right? So what happens is that when the temperature increases, the speed of particles increases as well. So what happens then? So more frequent collisions occur, which means greater pressure exerted. Is it clear, everybody?
Yes. So can you give a minute to write this down?
Yeah, sure, why not? So a lot of you might have pressure cookers in your home. Do you have pressure cooker? Where your mom makes food?
Yes.
How does that work? So you put food inside, like the ingredients, and then seal it off, becomes a container, and then heat it up. So within that, temperature increases, the air particles collide, create more pressure, helps in faster cooking, no? Is it clear?
Yes.
All right. Now, you guys have written this. Should I go on now?
No, sir, just a sec.
Okay. Okay. So, let's then talk about the movement of gas molecules or atoms. Okay. So there was a scientist. He was known as, I don't know who, Brown, but basically he gave this concept of Brownian motion. What he did was he put in a container there was air particles and some smoke particles, which are of course microscopic. So he also used a microscope to look at them. And then he also, put a light source. What he basically witnessed was that, so this is the microscope view. He witnessed that the smoke particles are moving randomly like this. Is it clear? All the particles are moving randomly. So he realized that basically the microscopic particles move randomly and collide with not only the walls of container but also the neighboring particles. Is it clear, everybody? So this could also happen in both could happen in both liquids and gases. So that's basically something you should know, right? Okay, in 10 minutes the the class will automatically shut. You need to rejoin. And of course, when you increase the temperature, the collisions will be faster. So this is an evidence, right, that these are like very light, fast-moving particles. Okay, just like that. Okay. Now, there were 3 different scientists who worked on gases and realized the relationship between volume, pressure, and temperature. Okay, so we're going to learn about each of them. First scientist produced the Boyle's law. And then we're going to look at the Charles law. And then we are going to look at the pressure law. Okay. So the Boyle's law states that pressure is inversely proportional to volume if temperature is kept constant. What it means is that this pressure is inversely proportional to volume. So if you draw a graph, it would look like you have pressure, you have volume. It would look like this. For this to happen, you must keep the temperature constant. So it means if you apply some pressure, like you're pressing something, so automatically the volume is going to decrease. If you release the pressure, so pressure is less, the volume is going to be more. Related to this, we need to learn this equation where we know that pressure, if you remove this, you multiply volume there. So PV is equal to constant. And this means this constant is the temperature. So basically PV, P1, V1, we can compare 2 different conditions like this. Which means that when the gas is at a certain pressure, it will be at a certain volume as well. But if you change the pressure or volume, it will also affect the pressure or volume, depends on what is changing. Is it clear, everybody? Now, Charles' law states that temperature is directly proportional to volume if pressure is kept constant. Which basically means that, hold on please, hello, काजन साहब मुझे 10 मिनट दें प्लीज़. जी वालेकुम अस्सलाम. काजन साहब मुझे 10 मिनट दें प्लीज़. Okay, so temperature is directly proportional to volume if pressure is constant. Now if you draw the graph for this, so you would want to keep the volume here, temperature here. So basically this will cause it to show you a straight lines that start from origin. Now this is a classic example of hot air balloons. Have you seen them? Have you traveled on them? Nobody has. So hot air balloons is like you heat, you burn something, right? A gas or something. And then because of the temperature, the balloon basically fills up and it becomes really big. So volume increases. That's why it goes up, right? Similarly, in pressure law, it states that pressure is directly proportional to temperature if volume is kept constant. Which means pressure is also directly proportional to temperature, and if you if you make a graph, it would look like this: pressure in pascals, temperature in kelvins, and this would cause you to have something like this. Is it clear? Everybody, any questions here?
Sir, what is PV equals to constant in the Boyle flow?
PV means this is like a relationship, right? Here. So if I want to remove this proportionality, I would have to write it as P equals to, let's suppose, K, a constant, times 1 upon V. Don't you think so? So if I multiply V there, so PV will be equal to K, which is the constant. Is it clear? Like that.
No, sir.
Whenever you have to remove this sign. You have to introduce a constant. Here it is K, let's suppose, right?
Okay.
So when you multiply this V with P, it will be PV. K will be left on the other side, which is the constant. Okay, Raviz, do you understand this?
Yes, sir. The meeting ended. Like, I voice cut in the end.
Okay, I was saying that basically, if you look at this equation, right, you gotta remove the proportionality sign. So P will be equal to K. Let's suppose K is the constant, times 1 upon V, right? Because there is 1 upon V already, right? So when you multiply V on the other side, it will be PV equals to K, which is the constant here. So it means if you multiply pressure and volume, it will be equal to some constant. Is it clear?
Yes, sir. And what about PV?
And about what?
P1 and V1 equals to P2.
So I said basically when, like, if a gas is at a certain volume like P1 and V1 and equals to K2, when you're looking at the same gas, it is at like oh no, what did it happen? Okay, P1 and V1 is equal to K. So you're looking at the same gas but at a different pressure, then it will have different volume. So it is also equal to the same constant because constant doesn't change. When you equate this, you'll get an equation which is P1 equals to P1 V1 equals to P2 V2. Okay?
I know, sir. Basically,
Like suppose there was a gas at say 100 pascals and it had a volume of 20 meter cube. Okay? So then you basically change the volume to of the same gas as 40 meter cube. You want to know what is the pressure now, okay? Because they're related. So what you're gonna do, you're gonna put it in this equation. Like pressure was 100 times 20, and now we want to find the new pressure when the volume increased to 40. So the new pressure is going to be like, I don't know, 50 pascals. Is it clear?
yes.
Yeah, like that. So it's basically comparison of the same gas when something changes, either pressure or volume. Then you can actually find the new volume or new pressure. Is it clear?
Yes, sir.
Okay. Now the last thing we're gonna do today is basically changing Kelvin scale to Celsius and vice versa. Okay, so they have a pretty simple relationship. So you should remember that the temperature in Kelvin is equal to the temperature in degrees Celsius plus 273. All right, like for example, if I want to know what is the boiling point of water in kelvins. What I'm going to do is I'm going to write the temperature in kelvins would be equal to, what is the boiling point of water in degrees Celsius? Anybody knows?
100.
100. So we're going to write 100 here plus 273. So it's going to give us 373 kelvins is the same temperature as 100 degrees Celsius. Is it clear?
Yes.
Same goes with the melting point of water in kelvins. So if I want to find it, I will do temperature in kelvins would be equal to 0 degrees plus 273. So that means that 273 kelvins is equivalent to 0 degrees. Is it clear? You can also change degrees Celsius into like kelvins into degrees Celsius. That's the same way you can do. Let's suppose they say, okay, change 20 Kelvin into degrees Celsius. So what you're going to do, write 20 equals to temperature in degrees Celsius plus 273. When you take it there, it will be 20 minus 273. So in temperature in degrees Celsius would be 20 minus 273 is minus 253 degrees Celsius. Is it clear?
Yes.
Exactly right. So this is how this works, and in the next class then we are going to look at the the thermal properties, and then we'll see. Okay, any questions now?
Sir,
Yes.
sir, we don't do this with Fahrenheit?
Fahrenheit is not in CIA. Alright. Fahrenheit basically